Hello, everybody. I'd like to welcome you to today's special Dean's Distinguished Speaker Seminar. The seminar will be given by Professor Spyros Pandis, who is in the Chemical Engineering Department of the University of Patras in Greece and co-director of the Center for Air Quality and Climate Change in the Foundation for Research and Technology. He received his PhD from Caltech in 1991 and joined the faculty of Carnegie Mellon University in 1993, and then moved back to Greece in 2004. And since then, he has been faculty at the University of Patras. His research includes theoretical and experimental studies of atmospheric chemistry as it relates to urban and regional pollution and topics related to global climate change. Professor Pandis has published over 300 peer-reviewed papers, and he is the author, together with Professor Seinfeld, of Atmospheric Chemistry and Physics, which is a textbook that is widely used around the world. He received many awards, among them the Fuchs Award by the International Aerosol Research Assembly, the Whitby and Sinclair Awards by the American Society for Aerosol Research, the Cecil Award in Environmental Engineering by the American Institute of Chemical Engineering, the Berknes Medal by the European Geophysical Union, and the Career Award by the US National Science Foundation. He has been the recipient of the Elias Chair in Carnegie Mellon University, the Kun Lee Award for Excellence in Chemical Engineering Education, and the Benjamin Thierry and University of Patras Awards for Excellence in Engineering Education. So without further ado, please give a warm welcome to Professor Pandis.
Thanks a lot for the introduction. So this will be kind of a literature review talk, and we will cover a few thousand years. We will be talking about particles in the air that we are breathing right now. And you will see that the talk will follow a little my career. We will use examples from the US and then Greece and Europe. But a lot of the conclusions and the tools are applicable around the world. So the particles that we are breathing right now have both inorganic and organic constituents. The smaller particles, smaller than 1 micrometer, are roughly half of the mass is organic, half is inorganic. The talk today will focus on the green part, the organics, which are thousands and thousands of different chemical compounds, and they are everywhere. So these particles are kind of visible to us because of the reduction in visibility that they cause. And they were kind of obvious to humans from a long, long time ago. So looking at the literature, and here I have to admit that I didn't do a superb job because the only ancient language I know is Greek. So I couldn't do a good job with the Chinese and the Assyrian and the Persian and other literatures. But in the Greek literature, the first kind of mention, or one of the first mentions of particles has to do with fire. And Hesiod was an ancient Greek writer that wrote Theogony. This is the history of the birth of the gods. And one chapter there is kind of Prometheus stealing the fire from the gods. Most of the ancient civilizations have a similar tale. What is special about this book is that Hesiod looks at the beginning of fire not as a major advancement for humanity, but rather as the descent of mankind into the present troublesome life. So that something bad was starting at the same time. Of course, this is kind of a painting by a painter in 1600. And, bad things started happening for Prometheus after that. The gods punished him by sending him to kind of a mount in Caucasus, and he had a bird there eat his liver every day. So really bad things happened from Prometheus. But we also know that combustion is one of the major sources of atmospheric organic particulate matter. So this is well known, right? Humans understand that when there is fire, there is smoke. Something that is more interesting in the ancient Greek literature is a mention of particles coming from cooking of meat, something that we call cooking organic aerosol. In ancient Greece, this was very important because this was the food of the gods. So the gods of Olympus were sustained by breathing the smoke from meat cooking. And this is, mentioned by Homer both in Iliad and Odyssey. So the ancient Greeks were smart. They were eating the meat, and they were giving the gods the smoke. That was kind of the idea. And here you start recognizing some signs of understanding of air quality. I have, with a red dot, Mount Olympus, where the 12 gods of ancient Greeks were residing. So they could understand that the smoke could travel from all over Greece to Olympus. There is even kind of another play by a Greek writer, Aristophanes, called Birds. And there the birds feel unappreciated, and they decide to go to punish the gods. And the idea of the birds to punish the gods is to build a city in the clouds that is called Nubikikilia. So this is kind of a weird name in Greece. And the city was supposed to be a barrier between the humans and the particles that they were sending to the gods and the gods. So this was kind of the ideas. The humans would cook meat, the particles would try to reach the gods, but then the barrier in the clouds would kind of prohibit the pollution to reach the top of the Mount Olympus. The gods would starve, and they would recognize the birds for their capabilities. So for those working on atmospheric meteorology, this is the first idea that you can split the atmosphere into layers. We call the intermediate the mixing height. And this is actually the first mention of geoengineering, right? How to change the planet. So for ancient Greeks, the two major sources of organic particles were fire and cooking of meat. So these kind of types of smoke were visible to people, and then with the Industrial Revolution, another source became evident, burning of coal. And I have two pictures from here, one from my hometown in the US, Pittsburgh. That was a clean day in 1925, and London, 1952. And again, burning of coal was the major reason for these extreme episodes of air pollution. Another source of organic particulate matter started showing up, especially after the Second World War, and this was cars. And you can see, pictures from Los Angeles where the ability of the atmosphere to cause reactions and cause oxidation of these organics became evidence, and the term smog was created. So coal, gasoline, and diesel were added to the mix. All these centuries, the idea for both the lay people and the scientists was simple. We have sources of emissions, mainly combustion and cooking, and these give primary organic particles. So if we look at the organics that are out there, I have them here in a scale of volatility. The idea was that we are emitting only particles that are non-volatile, and they disperse in the atmosphere, and they get removed. So that was kind of the mental model for these particles until the 50s. Then people started thinking that chemistry in the atmosphere may be producing secondary organic particles. And this is a picture of a chemist in Caltech named Ari Hagen-Smith. He's considered the father of organic chemistry. He kind of explained how ozone is formed in the gas phase, etc. But in a statement in one of his papers, he said that organic vapors, actually, especially those with double bonds, and I have cyclohexene there, and other olefins, they can react in the atmosphere and give non-volatile products that will condense on the particles, and you will have secondary organic particulate matter. This is a picture of Hagen-Smith in his organic chemistry laboratory. Please note that he's smoking. Okay, he was God as far as atmospheric chemistry was concerned at the time, so everybody forgot about primary particles and started thinking that the most important pathway is that we emit volatile organic compounds, especially olefins. They react and they give secondary material that condenses on the particles. So I was taught that this was the most important pathway in Los Angeles, at least. So now the framework changed. The emissions were in the other end, and then they were oxidized, and you are getting secondary particulate matter. Things started swinging the other way again because of a professor in Caltech named Glenn Cass, who found out that you can identify specific compounds in the organic aerosol, and these are linked to sources. For example, evoglucosan was linked to wood burning, cholesterol to meat cooking. So he used this technique to figure out where the particles in Los Angeles were coming from in the 80s. And these are kind of his results in 4 different places in Los Angeles. The secondary part is the white on top. So he said, no, it's mostly primary. The chemistry, even in Los Angeles, is responsible for 20%. And for the sources, the big surprise was that cars were responsible for something like 20%. In a place with 20 million cars, and a lot of them without catalyst. Diesel vehicles, which were only trucks, were responsible for another 20%. The big bar is in central Los Angeles. And another big surprise was that cooking, even in Los Angeles at that time, was actually more important than cars. So people were very skeptical about this idea that was now saying that it's mostly primary. But at least now the framework became more balanced. There are both primary particles, there is secondary material created by chemistry, and the emissions now are in the 2 ends, and there is chemistry giving semi-volatile material in the middle. Okay, so one needed to find some ways to describe the chemistry, and there are thousands of compounds, millions of reactions, thousands of products. The engineering approach that we took was say, okay, forget about all the complexity, just one product, and it is not interacting, it doesn't do anything. When you get saturation, it condenses. And we tried to simulate what was happening with that in Los Angeles. The results were so-and-so. These are results from that time that said even that with incomplete knowledge, we could make steps. Everybody, because of Hagen-Smith, was studying olefins. And according to this calculation, these are averages during the day in Los Angeles, olefins were responsible for just 5% of the organic aerosol. The top were aromatics, and toluene is separate from that were not studied at all. And there were also other surprises, that Los Angeles, a place with very little vegetation, biogenics were important precursors. So this incomplete work started people kind of taking a look at precursors that were not studied at the time. A major breakthrough came by J. Odum in '96, who did something simple, that he assumed that instead of one product, you get two, not a big step, but the idea is that they interact, forming solutions in the particulate phase. So this could explain something that was unexplained at that time, that the yield that you get of particles as you react more and more, a given volatile organic increases, and you can see the fit to the data. However, Jay was a true engineer, so he parameterized everything with these partitioning coefficients, these kappas. So here are some of the problems when you use semi-empirical fittings to describe something that happens in nature. So when these coefficients were used to simulate what's happening in Los Angeles, they gave 0, that there is no secondary organic aerosol. And the problem was that these constants are really inversely proportional to the volatility of the organics, which are a strong function of temperature. And the experiments were done in temperatures above 40 Celsius. So extrapolating them to 20-25% was completely wrong. So when we fixed this problem and we actually introduced the real physics, the model started doing better. Okay, we moved to the 2000s. Our chemical transport models simulate what happens in the atmosphere in 3 dimensions. And this was kind of 2007. This was our attempt to simulate what was happening in the US at the time. So these are the predictions of organic aerosol at ground level in a summer month. And you can see what you expect, right? High concentrations in the New York area, and you can see some of the big cities in the country. There were a lot of measurements to compare these observations, and I have the measurements in the x-axis and the predictions of the model in the y-axis for the 4 different seasons. The red and the blue are different networks. The red is in the cities, the blue is in the countryside. You can see a lot of scatter, but some of the scatter is unavoidable. There are uncertainties in meteorology. We use the same emissions every day, even if things happen in a city. So this appeared to suggest that we had things under control at the time. And this was more or less the time that I was returning to Greece from the US. So I was thinking that we were almost done with this research area, that we knew enough to reproduce what happened. What the model was doing, right, looking deeper, was it was also predicting what fraction was primary and what fraction was secondary. The red here is all secondary, the blue is all primary. And you can see that in the southeast US that has a lot of forests, it was something like 60% secondary, but not in the cities. Atlanta was 50-50. And in Pittsburgh, kind of up there, it was 30% secondary, 70% primary. So this is why the model was giving answers that looked right. We compared this model to a lot of techniques that try to apportion the sources of organic aerosol. I'm not going to bore you. They look at the organic tracers, the metals, organic and elemental carbon. Please just look at the bottom. The yellow is the secondary part. So it varies depending on the technique, from something like 25 to 40%. The model was giving 25. So all of our techniques at the time were relatively consistent with the model. So it appears that we had solved the problem. And then science kept happening. At that time, there was a new instrument that was developed that is called the aerosol mass spectrometer. This is a superb kind of engineering and chemical design. It takes particles, it uses fluid mechanics to make them form a beam. They enter this kind of opening, and then there is a chopper that rotates and stops them. The chopper has an opening, and when the opening comes, the particles flow through, and there is a race. They are separated by size. I mean, they're flying in vacuum practically, so the smaller get first, and then they hit a surface where they are vaporized, and then they are ionized by electron impact, and then you can measure their size and composition continuously in a matter of seconds. So one of the things that this instrument could do was not only give the composition of the particles, but it could give the mass spectra of the organics. And you could see there from the different fragments how much oxygen was there. So with a number of techniques, one could separate what was the result of combustion and other primary sources and what was from chemistry. And these were the comparisons now with a model. The red is what was measured with this new instrument. The blue was what the model was predicting for different areas. And it's clear that in all areas, the instrument was saying that the particles are mainly the product of chemistry, while the model was thinking that they were the product of just emissions. So that was a problem because the mass was right. So that meant that the model was getting both the emissions and the chemistry wrong, right? It was getting the right answer because it was making multiple offsetting mistakes. Okay, that was agonizing for us, and we were responsible for some of the data because it meant that a lot of what we had done was wrong. So, this is kind of a powerful lesson, right? That when you have something like that, your models can get the right answer for the wrong reasons. Your model can still be consistent with all available studies, both in the laboratory and the field. And of course, to solve this issue, you need to go back and do everything from scratch, including new laboratory experiments, redevelop the model, go back to the field and use better techniques and figure out if you got it. So what had we gotten wrong about emissions? All assumptions, or everybody up to that point was assuming that what comes out of a car, a fireplace, etc., is practically non-volatile. So these are measurements that we did with colleagues in Carnegie Mellon from the exhaust of a diesel engine. We were just diluting it and measuring how the particles responded. On top is the dilution ratio, starting from close to 1, to the atmospheric dilution, which is close to 10,000. At the bottom is the concentration, and the y-axis has the emissions, either normalized or not. Notice, not only this line is not constant, right? That's if it was inert, because we're correcting for dilution, it would stay at 1, but it goes down to 0.2. That means that 80% of what is emitted by a car, a diesel truck, evaporates a few seconds or minutes after its emission in the atmosphere. So we repeated this for a lot of other sources. The curves change, but all combustion sources emit particles that are semi-volatile, most of them. The second thing that we did is that we put this exhaust in an atmospheric simulation chamber and turned on the light. And what we saw is that a lot of secondary material is formed. The vapors that go to the gas phase react, and then they give other now oxidized compounds that come back to the particulate phase. And you can see after 3 hours, there were more material from chemistry than from the emissions, right? These are after the dilution. That's why they are constant. The next thing is that we needed to go back to the lab to study, what was happening with the oxidation of the volatile organics. And the problem was that the measurements up to that place were at relatively high concentrations and at relatively high temperatures. Most of the chambers were outdoors, so there was a greenhouse effect, and they were kind of warm to hot. So we needed techniques that allowed us to control both the temperature, but also perform measurements at low concentrations. So this is kind of a picture of an atmospheric simulation chamber in Greece. It's a 10 cubic meter Teflon reactor full of UV lights around it. And there are a lot of instruments like the proton transfer reaction mass spectrometer that allows you to go below 1 part per billion and be able to do the measurements at low concentration. The same for things like the aerosol mass spectrometer to the right. So our ability to measure low concentration had improved by that time. So the new experiments now are taking place in this space, which is a lot more relevant to the atmosphere, and we don't need to extrapolate that far in a nonlinear system. So this was kind of the old framework, and now it became obvious that we are emitting organics everywhere in space, from low volatility to volatile, and we also have a whole lot of chemistry that changes everything that we emit. Our next challenge is, okay, how do you deal with this complexity mathematically? The best that we did in the beginning, again thinking like engineers, was to project this space with thousands and thousands of dimensions to a space with just one dimension. And we chose volatility as the space. So we developed a framework that you just have a volatility distribution of the organics from the different sources. And we found out that a logarithmically spaced was good enough for the interpretation of the experiments and the simulation. To describe chemistry in this framework, you just move material from bin to bin with whatever rule you can derive. So we rewrote the whole model. Our model is called PM-CAMEX. We repeated the simulation for that summer in 2001. It agreed again with the measurements, similar performance with the previous model. But what was special now was that it agreed with the instrument, because now we had this extra chemistry that was explaining why most of what we're breathing is not what comes out of the exhaust, but what is the product of chemistry. And this is quite important. I'm not going to go into this, but it is actually more toxic. The chemistry, as we have seen, tends to make a material that is already bad even worse for us. So let's see, how good this new model was doing. So we worked with sites in Europe. Let me rotate Europe. The model uses a weird grid. So for now we are in May, and it was predicting high concentrations in Northern Europe and kind of lower in Southern for that month. And, this is the comparison now with the measurements and the predictions in different parts of Europe. So something like 90% of the hourly data points were kind of within a factor of 2. So this is by no means perfect, but it is in the right direction. We had an airplane doing measurements at the same time. The model predictions with height are the black lines. The measurements are in red, and these are for the flights of the airplane. We had some problems, but they are within the uncertainty, so we could get the decline as we go up reasonably well. We got smarter, right? We didn't just compare the total. We compared the secondary. This is this oxygenated organic aerosol. And this is for a lot of cities and a lot of months. And the results appeared to be promising, that we had moved in the right direction. We have tried to do it also globally. Now these are results of the same modeling framework, but against 80 data sets for 84 places in the world for different seasons. And the left has the primary, the right has the secondary. And you can see a lot of scatter, right? In a lot of these places, we didn't have good input data for emissions, etc. For the right, you can see the model is still tends to underestimate the oxygenated organic aerosol. There are these points in the lower triangle. But what is surprising, if you pay attention to the color, the red is the summer, where the photochemistry is happening, and we are doing relatively well. Most of the points where we are underestimating the chemistry are during the winter, in periods where it's cold, it's not sunny, it's cloudy, it even snows. So this is a suggestion that there is chemistry happening even at low sunlight intensity in the atmosphere, and we appear to be missing it. The same is true during the night. We wanted to get better, right? These results were promising, but we could do better. And the idea is, instead of projecting all the chemistry into one axis, to use TO. And the second axis, the one that we chose, was the oxygen content of the molecules, the oxygen to carbon ratio. So chemistry in this space is that we are emitting mainly near the bottom of the graph. The biomass burning is a little up because it is a little oxygen. And you can see with the green what the chemistry does. It tends to reduce the volatility and add oxidant. And eventually, it starts breaking down the molecules. And eventually, if they have time, they all become carbon dioxide. So that's kind of the two-dimensional volatility basis set that we tried with Neil Donahue. In this, chemistry is a little like playing chess. You have all of these boxes in your model. And for example, you can have this as a reaction. Or when you reach the top, you can have this. So parameterizing chemistry has not been easy. And we have been trying different rules to do this, different rules of what different reactions do. And what we found is that, okay, how do you evaluate these? Our techniques had gotten even better. Planes are nice, but they move really fast, and also they cannot go too low near the surface. So we tried for a year a very different platform, a Zeppelin that you can see up there. So in the gondola below the Zeppelin, we had the instruments. By the way, this was almost 100 meters long, right? So this is kind of enormous. And its advantage is that it can fly even during the night. It's very easy to land and get instruments in and out. So you can see the students changing the instrumentation in the field of in the Netherlands. And we flew over Europe with this for a long time, doing different types of measurements. Organic aerosol was one of the targets. So we ran our model against all the data collected in the Zeppelin. And our problem is that there were too many versions of the model that agreed with the measurements. In the end, we found 7 versions of the model. My PhD student liked this old movie, The Magnificent Seven. So she called the 7 iterations of the model the Magnificent Seven. And you can see what they were predicting and why they agreed at the top with the average measurements. Again, as a scientist, you are troubled, right? Because you have 7 different good explanations of the same thing. As an engineer, you care more about what they mean about the sources. So one of the components was secondary organic aerosol coming from anthropogenic sources. So these were kind of the 7 predictions for northern Italy, the Po Valley. And you can see, they are not the same, but they are all around 23% plus or minus 5%. This is enough information to make decisions about these sources. Our biggest trouble was with secondary organic aerosol coming from compounds emitted by trees. There, 4 of the models gave 20%, the other 3 gave 40%. So this interaction of biogenic pollution or biogenic emissions with anthropogenic pollutants remains a major uncertainty. This was the secondary organic aerosol coming from alkanes and other compounds of intermediate volatility, not the volatile ones, and that was another 20 to 30%. They agreed here. This was what was coming from sources directly, the primary. It was only 5%, and they practically agreed. And this was what was coming from particles evaporating and reacting again, another 10%. So all of them agreed. And this was what was coming to the Po Valley from outside Italy. So they also agreed. So you can see, despite these different mechanisms, with the exception of the biogenic, the rest were still consistent enough to move forward and trying to make some decisions. And we're working on figuring out which one of the 7 is closer to the truth. The Zeppelin allowed us to also compare vertically over 1 kilometer over the Po Valley, and not only the mass, but we could also compare the oxygen to carbon ratio, which was both for the model and the observations around 0.6. That's a lot, right? There are 0.6 oxygens for every carbon atom in a big organic molecule. This is how oxidized it gets, and this is what the people in Italy are breathing. Very different from the hydrocarbons coming out of a car or a truck. Our next idea experimentally was something that all chemical engineers want to do, right? We learn a lot about our systems by perturbing the system and noticing how it responds. Changing the atmosphere is very difficult, even if we are trying it as humanity these days. But our approach was, instead of changing all atmosphere, to change a couple of cubic meters at a time. So what we do is that we have built a system that takes our chambers in the field. We use 2 of them, and we fill them with ambient air. And then in one of them, we introduce a reactant, or we change the sunlight, or we do something to it, and we observe the changes. You can see we have a whole lot of good PhD students, and we have cloned a couple of them because they work really hard. So the chamber looks like this as you are building it, and you can take it in the field. You can use either the natural sunlight or use the UV lights next to it. And to the right, there is a deployment of the chamber in the island of Crete. Our instruments are in the van next to it. And here is what you see in a typical experiment. So we put air from the city at a given time. We characterize it for some time. And then in this experiment, we just turned the lights on. So you can see in the control chamber, there was a small decline that was suggesting actually that the chemistry that was taking place in that one was leading to evaporation because we had diluted. But in the one where we had the extra chemistry, we form a significant secondary organic aerosol that is now realistic, right? Because it is the air of the city. You can study other forms of chemistry, right? This was the sulfate that was produced in this experiment. Not a lot, right? It went from 1.4 to 2.2 micrograms per cubic meter, but you can have inorganic processes too. So we have been doing these experiments around the world. I apologize because some of the letters don't appear well. So the blue bars here are the organic aerosol that was formed, and the colors next to them is what we expected based on the volatile organic compounds that were in the chamber. And you can see that there is a big mismatch, which means two things, that we are missing precursors, and these are, we think, compounds of intermediate volatility that are not measured routinely, and that we still need to work on our chemistry, that there are processes that make these secondary molecules that we still don't understand. So we're not done yet. I will go back to Greece to close the presentation. So these were measurements from a decade ago, but last winter the measurements were the same. So this is organic aerosol in the center of Athens. The numbers, if you look, are big, right? 50, 60 micrograms is enormous. The World Health Organization is suggested for all the particulate matter to have concentrations below 5. And here are just the organics that reach 40 and 50. What is fascinating are the sources of these, what are in color. So the red, which is for 43%, is wood burning for reasons that had to do with a financial crisis the last decade. We are burning wood for heating in Athens, and this causes the spikes. Then there is the black, which is the cars. So the cars are just 17%. And the brown, the 16%, is cooking. So the two major sources in Athens right now are biomass burning and cooking. The cars are 17%, and the green is transport from outside of Athens. So it's amazing that 3,000 years later, we came to the same result. So for cooking, we have spent a whole lot of time, right? Why do we have so much in Greece? And given that this is before lunch, I thought that I should prepare your appetite. So yeah, these are kind of our fast food, and you can tell that they are emitting a whole lot of organic aerosol. So these are the conclusions. As humanity, we have been, even without realizing, thinking a lot about smoke and organic aerosol. It's clearly that's a lot more complex than a few particles getting formed in combustion and getting in the atmosphere. What we are emitting is actually semi-volatile and evaporates most of it relatively fast. And then after it evaporates, the vapors can react and can come back to the particulate phase, but as a very different molecule. And the result is that unless you are behind a dirty car or a dirty truck, the air that we are breathing is very different than what came out of the emission sources. So it is clear that the atmosphere is a giant reactor that keeps processing these organic compounds that keep evolving continuously. And this makes it quite difficult to link the particles with their sources. We think that we are making progress simulating them, that the results appear more promising and they start fitting with all the observations. However, I had said the same thing 15 years ago in a similar talk. So please, science may prove us wrong again. And kind of the fascinating thing for Greece, but also other developed countries that have reduced their pollution, that cars and industry are getting out of the picture, and more traditional sources like biomass burning and cooking that have not been controlled are emerging as dominant. So you realize that this work was the work for a lot of colleagues. I would like especially to thank Neil Donahue and Alan Robinson, colleagues in Carnegie Mellon, a lot of very good PhD students and postdocs, and also collaborators, both in Greece and across Europe. And I will close with a nice picture from one of our campaigns. This is actually next to our field station in Crete. If you pay attention, you can see actually the PhD students taking a break. So you're welcome to visit Greece. We're a good place not only for vacation, but for science too. Thank you.
Thank you very much for an excellent seminar. The seminar is open for discussion. And if you have questions, please step up to one of the microphones. Please.
Hello. Thank you so much for a great talk, Professor Pandis. Actually, I have a question. Is regarding the, the last few slides talking about the source apportionment of the ambient particles in Greece. I noticed that there was a significant proportion from BBOA, which is indicating biomass burning, right? So its amount is even more than the OOA we just discussed about. So would you think there will be a fast conversion of the BBOA to the OOA? Because I regularly remember that you have a recent publication indicates that the BBOA after emission will quickly transfer into the background particles. So am I correct that the background particles includes those from other sources just because the lose of the distinct characteristic of the BBOA, or they are converted into OOA?
This is a very good question, and I kind of skipped over that detail. So you are right that the biomass burning particles, even during the winter, even during the night, because these spikes were actually at around midnight, right? So the emissions were starting after the sun was setting, and they were picked or they were peaking before people went to bed because they would extinguish their fireplaces, etc. And there are signs that they are reacting. Actually, the analysis gave two factors, right? The fresh and the reacted. But for this presentation, I added them both. But you are right, even during the cold nights, they are changing. And our measurements show that the new form that is the result of actually chemistry with nitrates, right? There are nitrate radicals, etc., as you know well. They're actually, their oxidative potential was twice as much as for the fresh. So you're right, it is happening fast, and it appears that the products are more toxic than something that is already quite toxic, right? Biomass burning organic aerosol is quite toxic. So I have added them up to make the story simpler. Thanks for the question.
Thank you so much. So one more small question. So may I have some idea what is the biomass burning particles comes from, mainly from Greece, for example? Is that like from any households or wildfire?
Yeah, so what we have seen, and this is true not only for Greece, but for all of Europe, that biomass burning is now the predominant source of organic particulate matter throughout the year. During the summer, you get wildfires, especially in the south, but then the wind takes them all over the place. During the winter, you have biomass burning for residential heating. In Greece, it's just extreme because it is burned in a city of 5 million people, like Athens, surrounded by mountains. And we found out that also in the spring and the fall, especially again in the south, people burn agricultural waste, right? It's an easy way to get rid of whatever was left from after you harvested, etc. So no matter where we have looked in Europe, even in the clean places, it is a major source. So it appears that after you get the cars under control, after you get the industry under control, the next kind of challenge is to get biomass burning, especially if you want to be as clean as the World Health Organization is suggesting that we should be. Obviously, the cooking is a local problem in cities that appreciate good food.
Thank you so much again, Professor Pandis.
Thank you. Are there any additional questions? Please.
Thank you, Professor Pandis. I would just mention, right, I come from Portugal, former researcher also, and we met before.
Yeah.
We have the same problems, exactly the same problems as Greece. So on the practical point of view, in terms of mitigation efforts from governments, so what are, from your side, potential solutions? I remember from my past years in Portugal as a researcher, a discussion on a European directive to control the emissions from exactly sort of households burning that is happening throughout the cities. Do you have any insights, more recent insights?
For some of them, the solutions are easy, right? Residential burning of wood in Athens, right, should be prohibited. The Greek government, unfortunately, taxes enormously all other forms of heating, right, from heating oil, you name it, and wood is not taxed, right? It should be obviously treated very differently. For agricultural waste also, it's really a waste, right? This is a valuable source. We should be doing something. For wildfires, it's a lot more interesting. Actually, because of Portugal, we published a couple of months ago a paper in one of the nature journals showing how a major fire in Portugal in July 2022 affected Greece, right? We are in two opposite ends. And the concentrations in Greece were twice the World Health Organization limit for a week because of a fire in Portugal, which burned for several weeks. So we showed how this fire actually affected all of Europe, including Scandinavia, etc. It took 10 days for the smoke to arrive. And that's a tough problem, right? How do you deal with wildfires? As far as air pollution is concerned, this suggests that we should put a lot more energy into it. And our conclusion there is that it's not only an issue for Portugal or Greece, but because these particles travel long distances, it's kind of a European issue, right? And it should be treated like that because what is coming out, all Europeans were exposed to it. So we estimated that there were more than 1,000 additional deaths in Europe because of that fire, all over the place, right, over a month. again, it's right, a rough estimate that shows that these have a lot more impacts to human health than is currently recognized. And also that it's not only the place of the fire, but because they can travel, especially during the summer without rain, etc., long distances. So people keep breathing them for weeks in different countries.
Thank you.
Thank you.
Hi, Spyros. About the Magnificent 7 biogenic SOA prediction, there are the variations. Can you elaborate more?
Can you repeat what type of SOA?
The biogenic SOA predictions in the Magnificent 7, there are some variations, and you mentioned that it's the largest group that had the group that has largest variations. Can you elaborate? Yeah,
this has been one of the surprises in that field that I just mentioned. The reason that a forest smells so nice is because the trees are emitting volatile organic compounds that smell so nice. Actually, globally, trees emit more volatile organic compounds than humans. And okay, a lot of these emissions are in the Amazon, or they can be in parts of Africa or Asia, but they are a significant source of compounds, and these compounds are very reactive. They have double bonds, and they also are relatively big. Things like the monoterpenes have 10 carbon atoms. The sesquiterpenes have 15. So they react very fast, especially with ozone, also the hydroxyl radical, and they give products that have generally low volatility. So they are excellent precursors for forming secondary organic aerosol. So trees need to be taken into account in most environments, because they contribute to the whole issue. And our suggestions have been here, thinking about solutions, that if you are in a polluted city and you want to plant trees that don't smell, right? These are the ones that don't emit, how can I say, a lot of VOCs. And in every climate, there are, right, the Mediterranean climate that I'm familiar with, there are trees that you can smell from meters, and there are others that don't. So if you want to plant, choose the ones that don't. They look as good as the other ones. But yeah, it has been one of the surprises, and in places like the Southeast US or in Central Europe, etc., that are quite forested, they can be responsible for a significant fraction of this secondary organic aerosol. Philosophically, it's when they interact with the humans, right? Because you need the oxidants to convert them to particles. So, because I did part of my PhD studying this, and it was the philosophical discussion, is nature bad, right? Is it punishing us by forming particles? When I realized that the trees on their own wouldn't form that much, kind of discussing it with a colleague, he suggested the idea that only God can make a tree, and only a man can make him regret it. That we add the human pollution to the trees, and now we create particles that are bad for us, and they make the trees bad for us. So it's kind of one of these interesting interactions of man and nature.
Thank you. Any last question? Well, if not, then please join me to thank Professor Pandis once again. Thank you.